historical biogeography models, or one specific model, for performing cophylogenetic analyses. By cophylogeny here, I mean cases where we have species-specific symbionts that are thought to co-diverge. So for example, we have pocket gophers here on the left, and they're species-specific chewing lice on the right. And we assume when our pocket gophers speciate that we also get speciation in the chewing lice. And in lieu of anything else going on, we assume that that we will get perfectly matching trees, but clearly we don't get that. So we want to know what's going on in this scenario. Why are these trees not the same when maybe in this null expectation we might expect them to be? And so this is sort of similar and has historically been related to other sorts of processes where we have this container tree and an interior tree. This happens in species trees, where the species tree contains many gene trees. In cophylogeny, which I just mentioned, as well as in historical biogeography, where we might have an area cladogram, and we want to know the species distributions in the past. And so today, I'm mostly going to be talking about these two and relating, trying to provide a rationale that we maybe can use some more statistical likelihood-based methods from historical biogeography to analyze cophylogeny. And so that sort of discordance is often attributed to, between those two trees, the interior and the container tree, is often attributed to different sorts of events. And shown here are the different sorts of events you might expect in the case of cophylogeny, where we have in the interior tree, you can have speciation, extinction, without co-speciation. You can also have a switch from one host to another, or a sorting event where the host speciates, and the interior tree only goes into one descendant lineage and not the other. And you can also have co-divergence, of course, that I mentioned before. And so in the past, these sort of parsimony-based methods do certain things to try and relate this to these events. And one of these is Brooks parsimony, which is originally designed for this sort of problem, but now it's more used in historical biogeography. So kind of furthering that rationale that these are similar types of problems. And so we might have species tree and an area cladogram, and we want to know where our ancestral species were in the past. So we might map that on there using Brooks parsimony. And then a further extension to this sort of methodology is now more commonly used in cophylogeny with something like Jane, where you have a black host tree and a symbiont gray tree, for example. We take those different events that I talked about, we assign costs to each of those, we try and map the gray tree onto the black tree using these events, totaling up the costs and trying to find the map with the lowest cost. And so all of these parsimony type methods have some pretty big limitations, especially this cost type analysis. We're assigning these costs, and this can lead to some biases, but it's also, I think, very difficult to assign serious biological meaning to these costs. You can get more than one lowest cost mapping. Related to that, you don't get any quantification of uncertainty, and so you don't really have any confidence about which one which map you should choose, or how confident you should be in that map. And of course, there's no way to account for unrepresented lineages. So when there's incomplete sampling of the host or the symbiont in the cophylogeny case, you don't know, you are not able to account for that incomplete sampling. So getting back to our historical associations, unlike cophylogeny, which is still kind of using this parsimony framework, historical biogeography has seen development as a lot of development as far as statistical mathematical type models. And so the idea here is whether we can use those models that have been developed for historical biogeography to try and learn something about cophylogeny. And so that's the main question of my talk. Specifically, I'm going to try and apply the DEC. Specifically, I'm going to try and apply the dispersal extinction cladogenesis model to cophylogeny. And so this model, if you don't know about it, estimates ancestral geographic ranges on a phylogeny. And these geographic ranges are treated as composed of these discrete areas. So shown here are 3 areas that could make up several ranges that a species might have. And then these ranges can change through antigenetic events, such as dispersal and extinction between speciation events, and then at speciation events, cophylogenetic events can describe how these are inherited by descendant lineages, these ranges. And so for our analogy with cophylogeny, we can treat our host tree as a sort of area cladogram in a sense, and we can use an extension of this model to break up time into epochs that are bounded by our speciation nodes of our host. So that way, we can only have host switches to certain parts of our tree that make sense with time. And then we can analogize dispersal as host switching in our model, and then extirpation as extinction, and try and estimate these rates using the mathematical machine of these models. And so this gives us some advantages, I think, over previous methods. Instead of assigning costs of events, we have prior distributions that can give us a sense of these event rates and how uncertain we might be about them. Instead of having many lowest cost mappings, we're only going to get one posterior, which is nice. And then related to that, we don't get uncertainty quantified in these previous methods, but now we get this nice quantification of uncertainty in our posterior. And so the question is whether this actually works. I think it makes a lot of sense given this history, but I think we really need to do some simulations and figure out if it works. So to test this, I used the tree ducking simulator that I developed. It's available on GitHub, and it simulates these sort of nested phylogenies. And so we might simulate a species tree, or we will simulate a species tree under a birth-death process to a specific number of tips, like this. And then within that large tree, we might make a second tree using another birth-death process, but this time bounded by the time spanned by that larger tree. Might look like that. And you can note that you can get transfers from lineages that are bound for extinction, which is as opposed to other sorts of nested simulators. And so the simulation setup using this simulator, we have 8 tips for each of our species trees, each of our host trees, and I have a pure birth setting, and so no extinction is occurring, and a birth-death tree where we have some amount of extinction. I set the birth and death rates such that we would get about the same length of tree on average. And then for our symbiont tree, I allowed no independent speciation or extinction to occur within that. And I set 4 different host switching rates that correspond to different numbers of events, with 0 being a sort of perfect match between our host and our symbiont tree, since there's no transfers and nothing else going on, and the 17.5 transfers, so more than double the number of tips, representing this sort of like the host tree and then just a random other tree. So for our results with just 50 replicates, so this is an ongoing simulation, so bear with me here a little bit. This is what we get, and as you can see, I think on the y-axis we have just the average number of host switches, so it's just our posterior mean of dispersal scaled to the length of the tree. And you can see that it's pretty similar in all of our cases, which is not what I expected to find. But so I thought maybe this is very sensitive to the prior. Maybe there's not a lot of information in the data we're giving the model. So I used an exponential distribution also to see if it changed a lot. And you can see that it does change a lot, which makes a lot of sense given the prior. So maybe there's some amount of this not enough data effect going on to really inform anything, since we get much closer to 0. Yeah, in all of our cases we get this. And so there are some limitations with this. So far I haven't really shown that it works very well. So more simulation I think is needed. But also, one reason I used only 8 tips was it does not scale well at all with the number of hosts. And it's very difficult to get the model to run with more tips than 8. We're also still unable to account for these unrepresented taxa, which I think is a pretty big limitation in these cases, where we might expect those taxa to have some amount of effect on what's going on. And so in the future, I want to keep doing some simulations to really further explore this, given that I did so few. And there's also the possibility that we just need a better model that better describes what's going on in these scenarios. Something maybe like Mariana Brega and Michael Landis's paper that came out on bioRxiv a couple of days ago. It's a sort of similar scenario, similar type of application of a historical biogeography model might be closer to what might work. We also, I think, need a more specific simulator that more closely matches what's going on than maybe the simulator that I currently have developed. So extending my simulator to more closely mirror what's going on, I think, is a good direction to take this. With that, I'd like to thank my lab and my advisor, Tracy Heath, and also Michael Landis for some helpful comments on the modeling portion, as well as Iowa State's high performance computing resources for letting me use a bunch of them, and funding, of course. Thanks.
It doesn't scale well with the number of species of in your tests. Is 8 an absolute maximum, or?
So the question was, it doesn't scale well. Is 8 an absolute maximum? No, it's not an absolute maximum. So the problem is that with the areas, the way you can only have a certain number of areas in these biogeography models because the number of ranges scales to the number of areas, which is a really bad scaling factor. So it quickly becomes like, there's like a million ranges or something, like with like 20 houses.